Yeah, so welcome students. So let's start our class. So this is MA415 Algebra, and today's lecture number 22. Okay, now recall that we are discussing about ideals, okay, and question rings. Yeah, maybe I can give some of the examples, and we're discussing about say an ice and maybe an ideal of having R, okay, and then we define this R mod I quotient ring, and this is what this is all these cosets of I belongs to R, okay, and what are the operations? So operation is R1I plus R2I plus, this is nothing but R1 plus R2 of I, okay, and R1 I product with R2 plus I as R1 R2 plus I. So these two are the operations, and we prove that if you have an ideal, then all different properties satisfied, and you can actually define these two operations, okay. And then that means this maps actually is a map from R mod I cross I mod I to R mod I, right? That closed under multiplication, okay. And there are some many examples you can also talk about. Yeah, I think the natural example, most natural example was you have Z and you have some ideal, say something in Z, okay. So you check that in Z is an ideal, and then you find Z mod in Z, which is actually is nothing but of the form this in so 0 plus nz means nz, and then 1 plus nz, and so on, okay. N minus 1 plus nz, okay. This is a very common example of this quotient ring, okay. And then we can talk about another example which I think I have already discussed, but let me discuss again. So this polynomial ring, okay. So this is a ring of polynomials with integer coefficients, okay. And then you remember we defined last time also, so we map say fx going to say f of 0. F of 0 is nothing but the constant term, and we ask that this map is an homomorphism, right? Homomorphism from z mod x to z, right? So this is a map from zx to z, okay. So this is a ring homomorphism that you can easily prove it, and I think we have discussed this thing. So and what was the kernel? So kernel also I think we discussed. So kernel of this homomorphism is nothing but something called the principal ideal generated by x, okay. So this ideal are called principal ideal generated by x by the element, okay. And also we discussed in last class that this kernel of an homomorphism is an ideal, right? So you can talk about the cosine ring. So the cosine ring will be this ZX mod, sorry, in the, this is the cosine ring, right? This will be the cosine ring, say R dash. Okay. Now maybe when we will discuss the isomorphism theorems of rings, then we will show that this is actually isomorphic to Z itself. Okay, that we will prove it later. Okay, so this is the cosine ring. So this way you can also define, um, find out these ideals and other things, and also the cosine rings. Now let us discuss some of the property of these ideals, because this ideal is going to play a very crucial role in our that topic. Okay, so now I think I will discuss about this isomorphism theorem, but before that I want to discuss some of the properties. So let me just assume that my R is I don't know the commutative or not. So in that case, I cannot say left ideals or right ideals or not other things. So in general, okay. So what I'm assuming that let R be a unital ring. Unital means it contains unit. Okay. And then I would like to define. So when I'm saying unital, I mean that the identity is not equal to 0. So this is not a this is not a trivial ring. Okay. So so maybe you can define some of the proper some of the other ideals. So definition. Maybe definition 1. Okay. So we denote these something you start with some set, say something A, okay, and then we denote these by ideal generated by this we call ideal generated by A. What is this? So this is the smallest. This is the smallest ideals of R. Okay, that contains A. So what does this? I mean containing. Okay, whatever you can say. Containing A. Okay, so this is ideal containing. Okay. And obviously you can say this ideal, this kind of thing exists. Okay, how do you prove it? So you know that if you start the set of all the ideals which contains A, that is non-empty set, right? Because R is inside that, right? And now you also know that, I mean, this is homework, you can do it, that intersections of ideals. So when I'm saying ideals, I mean it can be finite, infinite, it doesn't matter. Ideals is an ideal. Okay. So if you take intersection of ideals, so 2, 3, 4, 5, infinite, then it will become an ideal. So if you take intersection of those ideals containing A, so it's an ideal, and that will be the smallest ideal needed for you. So this is a simple definition. You can easily find out this is an ideal. Okay. So now let me discuss some more maybe definition 2 set. So whenever I say RA, what does that mean? So that means that it is kind of finite sums of, so kind of R1, A1, something, RK, AK, where your Ri's are elements of the ring, AI's are the element of the set, and your this K is a natural number. Okay. Yeah, whatever natural number. So what you're taking the finite sum of element of the form R into A. Okay, finite sum. And then the convention is that obviously this is I'm thinking in not equal to 5. For this, if A equal to 5, no, empty set, then RA is 0. This is my convention. Okay, by convention this is 0. Okay. For A not equal to 5, you have defined this. Okay, and also you can define the other. Also, you can define A into R by the other way, like A1, R1. Okay, some finite sum. So something, or see, maybe A dash, R dash. So these are different. You don't assume that this R1 equal to R1 is. It can be any arbitrary things. Okay, so something. L dash, L dash, okay, I dash, element of R, I dash element of A, okay, and L is a natural number. Okay, so this you can easily define it. So the question is that what can you say about this? Whether these are ideals or not? Okay, so think about it. Whether what can you say about both RA and AR? Okay, whether RA is ideal generated by something, if not ideal generated by something, is it the left ideal generated by something? Okay, to find out that. So this is homework. Check that this is an left ideal generated by A. This is a right ideal generated by A. Okay, so if you multiply by left side, it will be absorbing. Multiply by right side, right? So this is you can find out these things. Okay, and obviously you can define something called two-sided ideal. And what is that? This is nothing but by definition RAR. Okay, which is nothing but the ideal. You can easily check. And what does this mean? This is kind of you have some R1, A1, R1 dash, and so on, and something RK, AK, RK dash. Okay. So and the same thing RI dash are element of R. AI is element of A, and K is positive integer natural number. Okay, clear. Now you can easily check that this ideal is called this is a two-sided ideal. You can easily check it. Okay, from right side left side, if you multiply by element of R, it will absorb. Okay, and you remember we said this principal ideal generated by here for single element. But if it is not single element, suppose your A is this kind of A is not a single element. Okay. If A is not a singleton, more than one element, then you can say that I mean obviously there might be a common element that generated, but if you need more than one element to generate, then it is not a principal ideal. Instead, if you have finally one element, it's called as a finally generated ideal. Okay, in the case of finally one elements. Okay, so um, this ideal, this you can easily prove that um, RA is a leftal generated by AR is a right generated by A, and RA is the two-sided ideal. And in the case of if R is commutative ring, then what happens? Then they coincide. What does that mean? Then your RA is nothing but AR is nothing but RAR, and which is nothing but this the symbol. Okay, the smallest ideal generated by A. Okay, so these proofs are all simple proofs. I think you can do it in homework. Okay, so these are some basic definition of ideals, and maybe we can have some more properties. So so let me or should I give some examples so that you can understand. Um, See, commutative everything is this there. So you try to find out. So this is homework. Find out an example of this R and the subset A are such that they are different, they are not equal, okay, they are not equal, whatever. What we do it, you can easily find out. So, for example, you start with a non-commutative ring, okay, and what you know about non-commutative ring, which is one of the most important example, is a matrix ring, okay. So inside matrix ring, can you find out something or not? You know the matrix multiplication is not commutative, right? Okay, so this kind of example you can easily find out. So now let me do some properties. So some properties of ideals. Okay, so so maybe we can start with that. So let I be an ideal of the ring R. Okay. Then maybe this is property number 1. And then if I equal to R, if and only if I contains an invertible element or kind of unit, an invertible okay, so I must say unit, then otherwise you may feel that invertible with respect to addition or what. So I should say contains a unit. Okay, and the proof is simple. So how do you prove this kind of statement? So obviously if I equal to R, then because I assume that I equal to unital, I is unital ring, right? Then 1 belongs to R, which is I, right? So done, nothing to prove. So I can't assume it. 1 is also unit, right? Conversely, if say if U belongs to I is a unit, then क्या हुआ? Then for any R belongs to R, we have what I can write for any R. So we can write down R equal to R into 1, right? And because U is a unit, so there exists some U dash such that U dash equal to 1, right? For some U dash belongs to R. Okay. So you can write down these as U R U dash. Okay. But I know that U dash is an element of the ideal, right? So R U dash is also element of ideal, right? Yeah, because U is element to ideal, and ideal absorb the element from R, right? So R into U is element of ideal, and hence if you multiply, this is to ideal. When I am saying ideal, mean to say ideal. So then multiply by U dash, again it's an element of the ideal R, right? So what does that mean? So every element of R is an element of I. So R is a subset of I. Okay, and hence I equal to R, right? So if you want to show something is a full, some ideal is a full ideal. Full ideal means the full ring. Then you need to only show that it contains one unit element, right? Now if I assume that R is a commutative ring with identity, then question is that how many units are there inside a field? So field means you remember the meaning of field. So every non-zero element is invertible, right? So property number 2, let R be a commutative unitary ring then what happened? Then R is a field if and only if something happened. If and only if it has only two ideals. So what does that mean? If only R has only two ideals, so you can say also what are those things, namely the zero ideals. Zero ideal is what? Singleton zero. And the full ideals. Full ideal is what? R, right? Only two ideal. And then you can say that this is a field also. Okay. So this is if and only condition used there. So you need to put that in the both side statement. And now obviously we know something. We know that field means that every non-zero element is an unit, right? It's a unit that you know, right? That the invertible means unit. So it's a proof. So which part should we prove first? Let's say R be a field, suppose. Okay. Then we need to see that there is no other ideal other than zero ideals and R, right? Now how do show that? So yeah, so R be a field means what? So that means R contains the unit, right? And if you choose any ideals, then what are the property? Uh, so 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 then every non-zero element non-zero element of R is a unit, right? So there are two cases. If you start with a zero element, then the ideal generated by ideal generated by zero is what? The zero ideal, right? Now we'll show that the ideal generated by non-zero element is the full ring, right? So now if suppose your non-zero element is R, which is element of R, okay, and because R is a unit, so there exists some R dash belongs to R such that R dash equal to 1 as R is a unit. Okay, so R dash equal to 1, and so what does that mean? That means yeah, so thus so if we choose any ideals which contains, I mean any ideal contains some non-zero element, right? And hence it contains R. So any ideals which contains R is also contains 1. Thus, so done. So now you remember last theorem, what we proved in last property. The moment it contains ones, then it is a full ideal, right? So this is a proof actually. Now you have a converse part. So conversely, what you need to prove? Conversely, you need to prove that if it has only two ideals, then it has to be in field. Okay, so it is given the commutative ring. Conversely, so conversely, let R be a commutative unital ring. Let R be a commutative unital ring contains only two ideals. Okay, is that zero ideal and full ideal, right? Then we need to find out that R is a field. Yeah, so this my computer system becomes so slow, I'm unable to write properly. Okay, but let me try. Okay, now I need to show that R is a field. So what does that mean? That means every non-zero element of R is a unit. So let R belongs to R be a non-zero element. Okay, so if it's non-zero element, then I need to show that this is an field, right? Invertible, right? So now you take the ideal, let ideal I equal to ideal generated by I, the principal ideal generated by I, right? So this cannot be equal to 0 ideal, as are not equal to 0, right? So what does that mean? Thus that means that this I has to be equal to the full ideal, okay, by the property that it has only two ideals, right? So it has to be full ideal. So once it is a full ideal, then you know something, you know that um, you know that 1 belongs to R and hence it's an element of I. So you can write down 1 element of I. So what does that mean? So 1 will be equal to, sometimes there exists some R dash, that's the 1 equal to R into R dash, right? Because element of I is of this form, right? It is generated by the single element for some R dash belongs to R, right? So thus R is a unit be a, so this is arbitrary, so I am choosing arbitrary non-zero element, so don't assume that this is special. Okay, so R is the unit and hence capital R is a field. Okay, so this is the proof. So the field has only two ideals, there is no other ideals. Okay, so you can say something interesting directly from here, that suppose we have a field and if you have a non-zero homomorphism, uh, then from that field to any ring, then this kind of homomorphism is always an injection. Okay, injective map. What does that mean? So you can easily find out directly. So you can say the corollary actually is that any non-zero ring homomorphism from a field to a ring is always injective. It's always injective. Okay. So the proof is simple. Again. Oh my God. Become very slow. I am unable to write even properly. So let's see. So suppose we have an homomorphism phi from a field say F to any ring. Okay. And you know that F is a field means it has only two ideas, right? But we also show that the kernel of phi is an ideal of F, right? The kernel is always ideal, right? Now see, there are two options. Either this kernel is there are two options, right? So either the kernel of phi is zero ideal or kernel of phi is a full ideal. Sorry, yeah, full F, full ideal. Okay. Now you see, this is not possible. Why this is not possible? Because if kernel of phi is full ideal, that means every element is mapping to 0 there, right? That is the meaning of kernel, that every element of f is mapping to 0. But that means phi is a, so this is not possible, as phi is a non-zero homomorphism. Okay, homomorphism. Clear? If everything mapping to 0, that is a 0 common, right? So what does that mean? That means the only possibilities is kernel of phi equal to 0. And what does that mean? That means I hope you know that kernel of some homomorphism is 0 if and only that map is 1-1 map, right? Injective map. This is, I think, the property of group theory we have learned already. Kernel of group homomorphism is 0 if and only if it is a 1-1 map, right? Same thing is true for ring homomorphism also. Okay. So, so these are quite simple. You can easily find out this property, and yeah. So there are many other properties of ideals I should discuss. Okay, maybe okay. Maybe I will stop here because this system become very hard and I am unable to write it down. Okay, so let me stop here. Next time maybe we will teach a little bit more. Okay.